Greetings everybody, and today we're going to be evaluating this absolute abomination of an integral using nothing other than complex analysis. So yeah, this integral is really quite nasty. We have a logarithm squared on the denominator here, which is really not that nice, amongst other random stuff like e's and a pi squared over here. So yeah, I don't know if there's real methods to evaluate this, but it actually turns out that using complex analysis and contour integration is really quite nice for this one. And this integral is really built for these type of methods, and we'll see how that works out later. So I found this on Math Stack Exchange, so I'll link the link or whatever it's called in the description below, so you guys can check out the original source. But to get started with this, I'm going to introduce a substitution. In particular, I'm going to let u be equal to the square root of x. And the reason for doing this, we'll see that we're going to be able to get rid of this 4 here, which is what we want to do. So that means that du is equal to 1 over 2 root x, but root x is already u, so it's equal to 2u dx. So dx is just equal to 2u du. So plugging this in, our bounds are unchanged, so it's 0 to infinity. Dx becomes 2u du, and then we have u squared plus e, and then we also have log squared of x, so that's going to be log squared. X is going to be u squared, so let's write that in there. And then we also have plus 4 times pi, but squared. Okay, next thing I'm going to do, I'm going to bring this 2 down using the log properties, but because the log is squared, that's actually going to become a 4. So this is equal to now. We're going to get a 4 here in front of the log. We can factor it out along with this 4 here, and that's going to cancel with this 2 to essentially give a half here. Integral from 0 to infinity, and then we have u du, and then this is all divided by u squared plus e, and then we're left with the logarithm squared of just u because we took down that power, and then we're left with pi squared because we factored out a 4 overall. Okay, so this is what we have. Now, you may notice over here we have log squared u, and then we have plus pi squared. And this almost looks like a difference of perfect squares, except there's a plus here. But since we're using complex analysis, we can go into the imaginary or the complex plane. And this over here, notice we can kind of write this as a log of u minus I times pi, and then log of u plus I times pi. And you may notice one thing, let's just make it a bit more clear. Let's maybe replace these with absolute values as well. I want you to notice one thing. Log of absolute value of something, and then you have minus I times pi, and then plus I pi over here. This is basically what the complex logarithm approaches as we approach from above and below the negative real axis. So if this is the complex plane here, let's say we have our branch cuts running over here. So arg of z is on the interval minus pi all the way up to pi. Then as we approach from above, log of z is actually going to become above the branch cuts, we're going to get log of absolute value of z, and then plus I times the arg. But arg of z approaches pi there. And then below, log of z, that's going to be equal to log of absolute value of z, and then a minus I times pi because the arg there is negative pi. So actually, we can somewhat evaluate this integral if we have 2 paths that go above and below this branch cut, and that should be able to recover these factors in some way. And we're actually going to use this to form a keyhole contour, so we're going to have a little path that goes around here, and also a really big path that goes all the way around as well. So that's how we're going to do our contour integration. Next question is though, which function should we choose to contour integrate? Let's put it over here, and we're going to actually take f of z to be equal to, we have, well, basically the integrands here, so z over z squared and then plus e, but now instead of having this log squared of u and then plus this pi squared, we're just going to take log of z. and the squared, we'll see where that comes from later as well. But this is the function that we're going to take to contour integrate. We're going to contour integrate along here, and we should be able to recover these factors in some way, and then try to get back to our original integral, which I forgot to do. Let's call our original integral I, as we usually do. So this is the plan so far. Let's see what the contour should look like in this case. So we know it's on the negative real axis, so something like this, and we go around these little paths here. Let's say gamma, let's say this is sine 1 and sine 2, and then we do a little big arc, not a little big arc, a really big arc around it to call that gamma, and to call the whole entire contour C, and we'll traverse in the positive direction as per usual. So what do we know so far about this function? Let's check out the poles. So we know there's poles because the denominator can be equal to 0. First of all, for this factor, z squared plus e, where are the poles? It's going to be plus or minus I square root of e. It's up over here and down over here somewhere. So that's I square root of e, and down over here, this is negative I square root of e. Okay, so these are the two poles from that first quadratic factor, and we're actually going to get a branch point for our logarithm. So log has a branch point at z equals 0, and if you take the reciprocal of log, you're still going to get a branch point there. The logarithm also produces a pole, or the reciprocal of the log produces a pole, because log of z can be equal to 0, in particular when z is equal to 1. So right over here, probably. So that's when log of z can be equal to 0, hence we're going to pick up a pole on our function there. So 3 poles, so we're going to end up evaluating 3 residues pretty much. Okay, so let's write down some integrals. So we know that's, what do we know? We know that the contour integral over c can be written as the integral along side 1, plus the integral along side 2, plus the integral along gamma, and then big gamma, and all of this must be equal to 2 pi I times the sum of the residues, which we'll figure out later. Okay, now a couple of these integrals are going to vanish, in particular the integral over little gamma, that's going to vanish because we're going around the branch points, and that's something quite easily you can show, I think, if you just parameterize this. And same thing goes for this integral over big gamma, it's also going to vanish as our radius increases to infinity. And yeah, we've done these type of calculations many times on this channel before, so I won't cover it here. So all we're left with is that these two integrals, sine 1 and sine 2, these are actually going to recover our original integral I, and we also have to evaluate the residues of our function. So there's 3 residues to evaluate. So what we're going to do, let's jump back over to the left-hand side, and we'll start evaluating some integrals and residues and whatnot. So let's go down here, and we'll take a look at the integral over sine 1. So let's see what that evaluates to as we approach from above the branch cut. So that is going to become the integral. Now sine 1, that's going from minus infinity back to 0. Well, as we take the limit, it's going to approach this interval. Okay, and we're integrating our function, so that's z divided by, we have z squared plus e, and as we approach from above, well, nothing's going to change with these, they're just going to be as they are. And how about this log z here? Well, what happens to log of z as we approach from above? Well, it's going to approach log of absolute value of z, and then we're going to have plus I times the arg of z, so that's going to be pi. So that was what I was talking about earlier, and then we have a dz. So the next thing we could do, let's get rid of this negative infinity by introducing a bit of a remapping. So let's map a z to, I don't know, let's say negative u, so it matches the variables over here. So what is that going to give us? It's going to give us the integral from infinity now up to 0. So the bounds, the signs flip. Z is going to become a negative, so we're going to get negative u, and then divided by, z is going to turn into negative u, but if you square that, that's still going to be u squared, and then plus e. And then over here, we're going to get log of absolute value of negative u. But notice u is always positive because we're on the interval 0 to infinity. So log of absolute value of negative u is really the same thing as log of just our u. And then we also have plus I times pi. So that doesn't change. And dz, that becomes negative du. So let's put in a du here, and the negative can cancel over here. What I also want to do, let's flip the bounds a little bit. So let's introduce a negative out here, and the bounds can flip to 0 to infinity. So that's the integral over psi 1. What about the integral over psi 2? So that's going to be the integral. Psi 2 is running from 0 back to negative infinity. And then we're going to have z over, well, basically the same thing. But now with the logarithm, what is the logarithm going to approach? It's going to approach log, absolute value of z, and then minus I times pi because we're from below. Okay, and again, we want to get rid of this negative infinity, so let's introduce a remapping. So z maps to minus u. So we're going to get the integral from 0 to infinity. Z is going to pick up a negative, so negative u. dz is also going to pick up a negative, so those are actually going to cancel. And then this is over u squared plus e, just like before. And then by the same arguments, this should give us log of u and then minus I times pi. Because z is going to turn into minus u, but the absolute values cancels and everything. So we're left with log of u minus I pi. Okay, so that's what we have. Now, on the left-hand side of this equation, notice we're adding psi 1 and psi 2 together. So let's just go ahead and add those two together and see what we get. So this is going to give us, so if you take the integral over psi 1, and then you add it with the integral over psi 2, what are we going to get? Well, both of these integrals are going from 0 to infinity, so we just add the integrands together. So we have the integral from 0 to infinity. Let's take this integrands over here and just subtract off this integrands because we have a negative. So we have u over u squared plus e, and then log of u minus I times pi, and then minus u over u squared plus e, and then log of u, and then plus I times pi. And then all this ends with a du. So now we're going to try to combine these two fractions together, and this is actually how we're going to reproduce this log squared of u, because notice this fraction over here, the denominator is missing the plus I pi factor, and then the same thing over here, this fraction is missing the minus I pi factor. So to kind of combine the two fractions together, we just cross multiply, or whatever that's called, and then we should recover the log squared of u. So what should happen then is we get the integral from 0 to infinity. We're going to multiply this u by whatever's missing. So that's log u plus I pi. Let's put that down here. So we have u log u and then plus I times pi. And then we have minus u once again. And then we multiply by this missing factor, which is log of u, but minus I times pi. Okay, and all of this is being divided through by, well, basically everything combines into the denominator. So we still have u squared plus e, and then we have log of u minus I pi times log u plus I pi. Okay, but if you multiply those two things together, you're going to recover log squared of u plus pi squared. So let's write that down instead. So we have log squared of u, and then we have plus pi squared, and then du. Okay, so we've recovered the denominator pretty much. How about the numerator? What happens there? Well, if you expand it out, you're going to get u log u over here, and then minus u log u. And even though we got logs on the numerator, it's really nice because those are essentially going to cancel each other out. And so we're left with the u times I times pi. And then we have a double negative over here, u times I times pi. So really what we end up with, let's go back up to over here, is we get the integral from 0 to infinity of 2 pi I times u divided by u squared plus e, and then we also have log squared of u, and then plus pi squared. And this is really nice because that's basically the integral we had before, but it's just off by a little factor. So what can we conclude from all of this? Well, all of this is still equal to I. Now, if you multiply both sides by 2, you'll get that just this integral over here is equal to 2 times I. So if you move this 2 pi I factor out the front actually, let's switch it in over here. We know this integral was that was 2 times I as we said before. So this whole thing, we know that's 2 times I. So if you add side 1 and side 2 together, if you trace back all the steps, this should give us 2 times pi times I times 2i. So overall 4 pi I times capital I. So that is the result of adding side 1 and side 2 together. So if you add those two integrals together, you pretty much recover our original integral I. So that's basically the left-hand side done. And now it's on to evaluating those residues on the right-hand side. So yeah, these two guys over here, that's equal to 4 pi I times big I. Let's calculate the residues now. And yeah, that shouldn't be too tricky to do. So the residues, let's take a look at the residue at z is equal to I square root of e first, so this top one. So this is of the function f of z, of course. So what is this? Well, we have a quadratic factor here, so you can split that up into linear factors, and since it's linear, it's just a simple pole. So we just use the formula for simple poles. It's the limit as z approaches the pole of z minus the pole, and then you multiply by a function, which is in this case just a z divided by z, and then let's factor it, so z minus I square root of e, and then z plus I square root of e, and then we also have that logarithm on the denominator. So what happens now, these factors cancel. If you plug I square root of e into z, what do we get? We're going to get I square root of e divided by, over here we're actually going to get 2I square root of e, and then a logarithm of I square root of e, like so. So this and this is going to cancel, so we're left with 1 over 2. Let's put that on the next line actually. So we're left with 1 over 2 logarithm of this complex number. But that's not too tricky to do. We know the formula for logarithm of complex numbers. It's going to be log of absolute value of this guy, but that's just going to be log of square root of e. And then we have plus I times the argument, but what is the argument? It's just pi over 2. So plus pi over 2. So this is equal to 1 over, we have 2. We can bring the square root down, so that's going to be 1/2 log of e, but log of e is 1, so that's overall going to be 1/2. And then we have plus I pi over 2. And if you just distribute everything, you're going to end up with 1 over 1 plus just I times pi. So that is the residue at this upper pole here. So what happens with the -1? So if we have the residue at z equals minus I square root of e, well this is negative here, and we're actually going to turn this into a plus sign. So this is plus and negative here. So these factors cancel, and we're plugging minus I square root of e into here. So up over here in the numerator, we should have gotten the negative. Down over here, we get a negative 2 I square root of e, so the negatives are going to cancel, and really the only thing that's changing is this extra negative in this logarithm. But how is that going to change things? Well, as for this absolute value part, nothing changes, but the argument does change because the argument becomes a minus pi over 2 instead. So this is going to be negative, and then if you keep expanding, you're going to get negative. So the residue, I guess we can just sum it up in this way. The residue at a plus or minus I square root of e. What is that going to be? It's just going to be 1 over 1 plus or minus I times pi, which is quite nice. Okay, so those are two of the residues done. Let's calculate this very final one here. So that's going to be the residue at z equals 1 of, your function. so f of z. So this is actually going to be a simple pole again. You can Taylor expands log if you want to, and you should get some kind of linear factor there. But yeah, let's just use the formula for poles, or simple poles rather. So this is going to be the limit as z approaches 1 of z minus 1 times our function, so z, and then z squared plus e, and then log of z. Okay, let's if we plug 1 into here, we're going to get 0, and if we plug 1 into log, we're going to get 0. So let's use L'Hopital's over here. So this is going to be the limit as z approaches 1 of, we have z, let's see. So first of all, z over z squared plus e, that's not problematic, so we can just take the limit separately there. So z over z squared plus e. And then we're going to take another limit, so we can kind of split up the limits across the product. We have z approaching 1 of, we have z minus 1 over log of z. But this we can use L'Hopital's rule, as I said before. So this first limit, that should approach 1 over 1 plus e. So 1 over 1 plus e. And as for the second limit, if you differentiate the top, you're going to get 1. If you differentiate the bottom, you're going to get 1 over z. So overall, you're taking the limit as z approaches 1 of 1 over z, which is just equal to z. So really, this is going to be 1. So the residue at z equals 1 is just going to be 1 over 1 plus e. So let's write that down over here. So we're just going to get 1 over 1 plus e. Okay, so we've evaluated the residues, and we've figured out all the contour integrals, or the integrals that we need to. Now we just need to combine everything together. So what do we have in the very end? We have the left-hand side, which we found was 4 pi I times capital I, and the right-hand side, that's just equal to 2 pi I, times, we have the sum of the residues, so for the plus residue, so plus I root e, this is going to be 1 over 1 plus I times pi, and then you add the negative one, so 1 minus I times pi, and you also add this contribution over here of 1 over 1 plus e. There's some pretty interesting expressions over here. Let's combine these two fractions together. That shouldn't be too tricky to do, so we have 2 pi I. Actually, what we can do, let's cancel over here. So these cancel, leaving us with just a 2 on the the left-hand side. So we have 2i, and that's going to be equal to, we have these guys, if you multiply them or combine them together, we're going to get 1 minus I times pi, and then 1 plus I times pi. So if you just cross multiply, and then divided by the product down here. So that's going to be 1 and then minus I pi squared, but that's just going to be 1 plus pi squared. So these negative I pi's and this plus I pi, that will cancel. And then we also have 1 over 1 plus e that remains. So overall, let's do implication error here. So therefore I, that should be equal to, we have basically 2 over here divided by 1 plus pi squared, but if we divide by 2, that should leave us with 1 over 1 plus pi squared. And then we also have 1 over 1 plus e, but if we divide by 2, that should be a plus 1, or let's write it as maybe 1/2, and then 1 over 1 plus e. And then we are done. So this is actually the solution for our integral. There it is. Pretty interesting result though. We have pi's and e's mixed in, and they're on the denominator. We have a pi squared, and yeah, interesting things going on there. So yeah, this integral, it actually works out really quite nicely with complex analysis. As I said before, I'm not too sure if you can get this using real methods, or maybe there's some tricks or something that I don't know of, but yeah. If you guys know of any real methods for this one, let me know in the comments below. Otherwise, that's pretty much all for today. Hope you guys enjoyed this little complex analysis snack over here. Bit of a big snack, but yeah. hope you guys enjoyed. And yeah, up until the next one, have yourselves a wonderful day, and I'll see you everyone later. Bye bye.